Hello everyone, thanks for watching our presentation. We hope you all are doing well. Today I'm going to present our work, Chapter, Efficient Inference of TNNs via Channel Pruning. Here is the outline of my presentation. First, I'll go through the overview of DNNs and open challenges in deployment of DNNs on edge devices. Then I'll introduce some related works in this area. Followed by that is our contributions of this paper, and finally, I'll present our results and conclusions. Deep neural networks have achieved great success in many fields and have been applied to many real-life applications, such as object localization, object detection, autonomous vehicle, natural language processing, game AI, and so on and so forth. To achieve better performance, more and more complex models have been designed. For example, this figure shows the top 5 error rates versus the depth of the winning model. For ImageNet classification contest between 2010 to 2015, the x-axis shows the different models. The height of the bar represents top 5 error rate, and the dashed line indicates the number of layers in this model. As can be seen from this figure, the error rate has been significantly decreased from 28.2 to 3.57, while the number of layers in these models dramatically increased from shallow to 152 layers. This figure roughly suggests that more layers can be translated to higher accuracy. This figure here shows more statistics of those models. The x-axis shows the number of gig operations needed per inference, and the y-axis shows the top 1 accuracy achieved by these models. The size of the circle represents the size of the model, in other words, the number of parameters in the model. As we can see, in early years, researchers tried to design more accurate models while sacrificing the size and the computation requirement of the models. But recently, the goal is shifted to designing smaller, compact, and still accurate models. In other words, we would like to draw a small circle in the upper left region of this figure. The reason why compact models matters is because to apply these models in real-life applications, they need to be executed on some platforms at the end. In our work, we consider resource-constrained edge devices as our target platform because there are so many IoT devices around us and we want to utilize their computation power. There are 4 aspects of challenges need to be resolved in order to deploy DNNs into target edge devices while preserving their accuracies. First is the static memory requirements, because we at least need to fit large CNN models into storage-limited edge devices. Second is runtime memory requirement, because calculating and storing intermediate feature maps also incur large memory footprint. Thirdly is the computation capability, since we need to accomplish billions of operations within certain latency to ensure satisfactory user experience. And finally is the energy consumption, because accessing memory and conducting huge amount of computation are energy consuming, which poses a big threat on battery-powered devices. To give you an example, a quad-core ARM A53 chip can only run GoogleNet at 1 frame per second and consumes about 4.5 watts. This is under no constraint about power, storage, and with proper cooling. Many works have been proposed to resolve these challenges. One direction is to reduce hardware implementation cost per computation and per memory access, such as quantizing weights and activations, performing low-power multiplication with stochastic computing, and maximizing data reuse to minimize data movement energy. The limitation of these works is that the structures of DNNs remains intact, and they may not be the optimal model for the given task. The second direction is simplifying the structure of a trained DNN. This includes unstructured pruning techniques, structured pruning techniques, and low-rank approximation-based techniques. Unstructured pruning techniques such as optimal brain damage, weight decay, weight sharing, deep compression pipeline often result in sparse weight matrix, which requires special hardware such as efficient inference engine to fully harvest its potential. On the other hand, Structured pruning techniques, such as pruning kernels in convolutional layers or pruning entire layers, do not have such issue, but many of them require expensive training from scratch process. Low-rank approximation-based techniques, such as weight matrix decomposition and higher-order tensor approximation, are straightforward to be applied to individual layers, but not across layers. They effectively expanding each layer into 2 or 3 layers, which adversely impacts the actual inference time. On third direction, researchers are designing new network modules and structures. This includes both handcrafted designs and automatic neural architecture search. Handcrafted designs such as networking networks, ResNet, Inception module in GoogleNet, and Fire module in SqueezeNet are almost art. The design process requires tremendous insight about the target task itself and mostly a manual process. On the other hand, neural architecture search utilizes reinforcement learning and genetic algorithms to explore the design space, but they require huge amount of computations. Our contribution in this paper is that we propose CHAP'NN, which is a structure simplification technique for trained DNNs. We first show how it can be used to prune input channels and the corresponding filters of a convolutional layer, and then demonstrate a technique for exploring more pruning opportunities in ResNet-like models. To apply CHAP'NN to all the layers in a model, we first perform sensitivity analysis to decide how much each layer should be pruned. And finally, we prune the entire module and show better results compared to many prior works. Our motivation for targeting convolutional layers came from the fact that there are many redundant channels in convolutional layers, while the number of convolutional layers are increasing in many modern DNNs designed for vision-related tasks. At the same time, convolutional layer is the most energy-consuming and computation-heavy type of layer. Thus, it has the biggest potential impact if it can be successfully pruned. We also want our technique to be a structured pruning technique because in this way, not only the aforementioned 4 issues can be alleviated, more importantly, the benefits brought by pruning can be easily harvested by existing hardware and software libraries. Now let me introduce some preliminaries and notations before going to the details. The top figure here is the very basic LeNet-5 model. It consists of 2 convolutional layers, 2 subsampling layers, and 2 fully connected layers. Each conv layer takes a set of feature maps as its input. For the first layer, the input feature map is the input image itself. It then performs spatial convolutional operation on top of the input feature maps with a set of small kernels to generate a set of output feature maps. Each feature map is also called as a channel, and each kernel corresponds to one output channel. Conv layers are responsible for extracting features such as edges or shapes from the image. Subsampling layers usually perform max pooling operation in small regions of the input feature maps to generate smaller output feature maps, so the number of neurons fed into the next layer can be reduced. Fully connected layers simply connect all input neurons with all output neurons, and it is usually used to generate the final classification. In the LeNet-5, there are the probabilities of the 10 classes. There are many redundant channels in conv layer. Such redundancy is necessary during training to achieve high performance, but they can be removed during inference, and removing them can significantly reduce the model size, computation, and memory requirements. Now let me give you an example of what we mean by redundant channels. The figure at the bottom shows some feature maps generated by the first conv layer of VGG16 model. They look very similar to each other, and many of them could be pruned without impacting the final results. Now let's dive into the details. This figure shows 2 consecutive conv layers, layer L-1 and layer L. These slices represent feature maps or channels, and together they form the input and output tensor of a layer. The blocks represent the kernels of layer, and in fact, each block consists many slices as well, and each slice corresponds to one input channel. For simplicity, we assume there is no subsampling layer between these two layers, but a subsampling layer can be added without affecting the correctness of our technique. The goal of channel pruning is to identify and prune redundant channels of the input tensor of the target convolutional layer. Once redundant channels are identified, the corresponding feature maps, kernels of the previous and current layers, can also be pruned, thus reducing static runtime memory requirements, computation, and energy consumption. For example, if the target layer is L and this orange channel is identified as redundant, then the kernel of the previous layer that generates this channel can be pruned, which is shown as the orange block, and a part of all kernels of the current layer, which is shown as orange slices, that correspond to the redundant channel, can be pruned as well. This channel pruning problem has gained attention recently with a lot of recent publications, and we will compare against these works. Our technique considers the intermediate values generated during the convolution operation. This figure shows the process of generating the J's output feature map. Each element of out J of this feature map is generated by sum of the OJC elements of the intermediate output feature maps, where the index C, ranging from 1 to the number of input feature maps, each intermediate OJC element is generated by performing convolution operations between the C's input feature map and the corresponding parameters of the J's kernel. The entire process is expressed by these two equations. Now let's consider one OJC vector. If a subset of OJCs from the OJC vector can be found such that every element in this subset can be approximated by linear combinations of the OJCs outside of this subset, then this subset is redundant and can be pruned, and the remaining OJCs can be scaled accordingly, and their summation can be used to approximate the original out J element. This idea translates to pruning the corresponding channels and kernel weights, and scaling the remaining kernel weights. The redundancy analysis in the previous slide was for one OJC vector, which corresponds to only one output element of one input image. If we want to generalize such analysis, it needs to be extended for all elements in the output tensor and across all input images. Thus, our channel pruning problem can be formulated as identifying these redundant subsets for all elements in the output tensor and across all input images. The extension of such analysis is done by extending OJC vector into a CLN by N matrix A. Specifically, matrix A is generated by taking N samples from various spatial locations, output feature maps, and training images, and then extending the column vector from these samples along the column direction. The resulting matrix A looks like the following, where N is the number of samples, and ideally, N equals to the number of training images times the number of output channels times the size of output feature map. CLN is the total number of input channels. Thus, the problem of identifying redundant channels in the input tensor becomes identifying the redundant rows in A. We solve the problem of identifying redundant rows in A by solving its inverse problem, which is identifying the most CLN minus N representative rows in A, which is in turn can be solved by pivoted QR factorization algorithm. The algorithm is shown in the slide. The input of the algorithm is the matrix A and M, which is the number of redundant rows need to be identified. Here we assume we know the value of M, and I will explain in the experiments how M is determined. The output is the indices of the identified redundant rows, which is equivalent to the indices of the input channels that can be pruned. Besides the traditional layer-by-layer CNN architectures, ResNet architecture has emerged in recent years to provide better performance. It was the winning model of 2015 contest and was the first model achieved better than human performance. The idea of shortcut paths is adopted by many later models. In general, ResNet-like architectures consist of multiple bottleneck blocks, with each of them has 3 to 6 bottleneck units. Each bottleneck unit has 2 or 3 convolutional layers and 1 identity or projection shortcut path. For example, this figure shows a 34-layer ResNet with 4 bottleneck blocks and 16 bottleneck units. The solid arcs represent identity paths and dashed arcs represent projection paths. Now let's zoom into 2 of these bottleneck units. In this figure, Unit 1 has a projection path and Unit 2 has an identity path. Conv layer 1, 2, 3 are just normal convolutional layers as we have seen before. In prior works, only Conv 2 and 3 layers in each unit are pruned. This is because for units with projection paths, they cannot prune projection and Conv 1 layer simultaneously. And for units with identity paths, pruning Conv 1 layer will cause misalignment problem when merging its input tensor with the output tensor of Conv 3 layer. We will show how our algorithm can be applied to all the 3 convolutional layers for more pruning opportunity. The technique we propose is to prune layers in backward direction and propagate the choice of capped channels so the shortcut path is applicable. And later, when pruning the Conv 1 layer in each unit, considering either the propagated choice of capped channels or the projection shortcut path at the same time. For example, for Unit 2, we know there are some channels need to be preserved because those indices are propagated back from later layers. So we don't prune those channels when pruning the Conv 1 layer. After pruning, the remaining channels should be a superset of the channels needed by the later layer. So we use channel sampling to select those out. For Unit 1, when pruning Conv 1 layer, we just need to do the sampling from both the projection layer and Conv 1 layer at the same time. Now let me present our experiments and results. Recall that the pruning algorithm receives an input parameter specifies the number of channels to be pruned. So we first perform sensitivity analysis to determine this parameter for each layer. The sensitivity analysis is performed by applying the technique to each layer independently and recording how the accuracies are impacted when various number of input channels are pruned. Then we set the pruning target for each layer based on its sensitivity and prune the entire module. And finally, we compare our results with these recent works. Here are the results of the sensitivity analysis for VTG16 model. It shows the sensitivity curves of 5 representative layers, ranging from early layers, which is shown as blue and green curves, to later layers, which are shown as red and purple curves. Because these layers have different number of input channels, the x-axis represents the percentage of pruned channels, and the y-axis represents top 1 and top 5 accuracies. From this figure, we make 2 observations. First, early layers have lower rates of drop in accuracy, with increasing percentage of pruned channels, and we think this is because features extracted by early layers are simpler, so it is easier for them to be approximated by linear combinations of the others. This behavior suggests more channels may be pruned from early layers. Second, some layers, such as the purple and red layers, are more sensitive to pruning than others, and we need to identify these layers and prune less from the sensitivity layers. This figure shows the sensitivity analysis for ResNet 50 model. Comparing it with the sensitivity analysis of VGG16, they look similar in general. However, layers of ResNet 50 are much more insensitive to pruning than those of VGG16. This is because a ResNet model with n bottleneck units effectively has 2 to the power of n passes from the input to the output, and many passes are intact when a single layer is pruned. Information can still flow through these passes, thus accuracy stays relatively high. So our overall strategy for pruning a given model is to prune all its convolutional layers in backward direction and set the pruning target for each layer according to its sensitivity. Specifically, for layers that are insensitive to pruning, we prune 50% to 70% of their input channels and not more, even if accuracies are still high. This is because the sensitivity analysis is performed independently for each layer. Therefore, the interlayer behaviors are not reflected, and we choose to leave some margin for later layers. For layers that are sensitive to pruning, we prune up to 50% of their input channels so that accuracies do not degrade too much. We also know that the fine-tuning is performed after pruning each layer to recover the lost accuracy, which has been done in many other works. This figure shows the comparison between our work and many prior works in terms of both number of computations needed per inference and top 1 and 5 accuracies. Some statistics are calculated by ourselves and others are borrowed from other papers. The x-axis is computation requirement and y-axis is accuracy. Thus, if point A is on the lower right side of point B, it means model A is clearly inferior than model B because it needs more computation but still generates worse results. But if point A is at upper right or lower left of point B, it is not easy to say which one is better. According to the figure, the pruned model generated by our technique is better than 3 prior works in terms of both computation requirement and accuracy. However, it is not obvious to judge which pruned model is better for the remaining works, but we will compare them with a unified metric that considers both of these 2 aspects. Similarly, for ResNet 50, the pruned model generated by our technique is better than 3 prior works in terms of both computation and accuracy, but the result becomes not obvious when comparing the remaining 3 works. To overcome the affirmation problem that pruned models cannot be easily compared, we introduced the overall score metric to take into account both accuracy and reduction in computation. The overall score is defined as shown in the equation, where number F indicates the number of flops, T1A and T5A indicates top 1 and top 5 accuracies. The above score emphasizes that more reduction in computation with less degradation in accuracy are desired for each pruned model. Thus, a higher overall score is better. Clearly, with the statistics listed in the table, our pruned model achieves the high score. In fact, we even try to assign different weights of either value 1 or 2 to the 3 terms in the equation, and CHAP'NN consistently maintains a high score in both VGG16 and ResNet 50. We also tested actual inference time on a GTX 1080 Ti GPU and achieved 1.87 times and 1.57 times reductions, respectively. As a conclusion, in this paper, we introduced a new channel pruning technique which specifically targets at convolutional layers. We propose techniques to explore more pruning opportunities in ResNet-like architectures. And finally, we showed that techniques can significantly reduce both computation and actual inference time while preserving the original accuracies, and overall, better than many recent prior works. And here are the references. Please feel free to ask any questions. Thank you.